Hi, everyone. What we're going to be talking about today are horizontal limits. In other words, limits as we approach positive and negative infinity on the x-axis. So we have many theorems about limits that we'll be working with. And when we get into these, I'll just show you the rules here and how they work. Some of this is going to be old news, things that we did in pre-calculus. Some of it's going to be new. So first of all, let's take a look at this first example, okay? And what we know, let's look at our little rules. When we have a number over x, as that number gets larger and larger and larger, as x gets larger and larger and larger, the overall fraction gets smaller and smaller and smaller. So think about this. If you had a pizza and you were sharing it with just one person, with one person, you would have half of the pizza. But as you started sharing it with more and more and more and more people, you would wind up getting less and less pizza until eventually you pretty much got no pizza. That's really what this is telling us. So if we look at a problem like the first example, we have the limit as x approaches infinity. So we have 2 minus 1 over infinity. And what we know from that is that this fraction will essentially approach 0. So the limit as x approaches infinity of this function will be 2 because that approaches 0. So let's take a look at the next one. And this is where we have some review. So we're taking the limit as x approaches infinity, and we have this rational function. So the rule of thumb is to divide by the highest power of x that appears in the denominator. So obviously it's just x to the first. So we're going to have every single term in the numerator and denominator divided by x to the first. When we look at this, we will evaluate each fraction and take the limit essentially of each fraction. So if we look at this, the x's would cancel out. So we'd be left with 5. 7 over x as x approaches infinity approaches 0. So we have 5 minus 0 over. These x's cancel out and we're left with 4. And this approaches 0 as well. As x approaches infinity, the limit of this would approach 0. When we clean this all up, we can clearly see that this function would approach 5 over 4 as x approaches infinity. So in other words, if we were graphing this, we would have an asymptote at 5/4 or 1 1/4, so it would be approaching 5/4 as x approaches infinity. Our second example, you might notice, looks very, very similar, except for the fact that we have negative infinity. We are approaching negative infinity. So when we do this problem, and we take the limit as x approaches negative infinity, it will be very much the same process, the only difference being that we put a negative out in front of our work. And so now we look to our denominator. We have x to the fourth, which is our largest exponent. So we will divide each and every term by x to the fourth and then evaluate. So we go through every single one, dividing each one by x to the fourth. And then we evaluate the limit as x approaches negative infinity of all of these. Okay, so plus 3 over x to the fourth. I don't know why I wrote x squared there. Anyway, if we look at these will cancel out and we'll just be left with 6 over 0. These will cancel and we'll be left with x squared. This doesn't reduce at all. Here we are left with 7. X squared over x to the fourth leaves us with x squared in our denominator, and this doesn't reduce at all. So looking at these values, the first fraction we get is 6 over infinity. So this approaches 0. 3 over infinity squared also approaches 0. Minus 7 over infinity to the fourth is 0. In our denominator, we would be left with 7 plus 0 plus 0. When we put this all together, we have negative, look at our numerator, 0 over 7, which is 0. Okay, so the only difference there is really we have to put that negative out in front because of the negative infinity that we were approaching. Okay, examples 4 and 5 are pretty similar to what we've been doing. We're going to infinity. The only thing I might suggest is a little rewrite where you put the values in decreasing order of their exponents. So 3x squared plus 2, and then go ahead and divide by the largest degree in the denominator. So we have divided by y squared over y squared. And then same thing here, 5y squared over y squared plus 4y over y squared. And you might be remembering a rule from last year where we said if the ratios of the lead coefficient, if the exponent's degree in the numerator was the same as the degree in the denominator, then the limit would simply be the ratio of the lead coefficients. And that's exactly what's happening here. So what we get from this is that our limit is approaching negative 3/4. So why don't you go ahead and pause that video, FOIL the denominator here, and then take the limit, and we'll see if we get to the same number. So go ahead and pause that video. No cheating. Pause it. Okay, so when you did FOIL that out, I hope you noticed that we had the same degree in the numerator and denominator. So these are all going to zero out, but we get 4 over 2, which is 2. Hopefully you got the same answer and you were able to do that pretty easily. Okay, things are about to change a little bit. So for problems like this, if you notice, we have a radical in our denominator, but we don't have a radical in our numerator. So in our denominator, what we have to do is we have to divide everything under the radical by x squared. In the numerator, okay, sorry, I got interrupted there. But what we have to do for our numerator is we actually have to divide the numerator, because it's not under a radical, by the square root of the biggest exponent, the variable with the biggest exponent in our denominator. That's under the radical. So we'll be dividing the numerator by x, but the denominator we will be dividing by x squared. So our numerator will look like this, negative x divided by x. And again, the way we got that was we took the square root of the variable with the biggest exponent under the radical. And in the denominator, we're going to keep it under the radical, but we will be dividing by x squared. And we'll evaluate very similar to how we just did. So negative x over x reduces, so we have negative 1 in our numerator. 4 over x squared would reduce to, or the limit would approach 0. X squared over x squared is 1. We take the square root of 0 plus 1, in other words, the square root of 1, which is 1. Our numerator became negative 1. So what we found is that the limit as x approaches infinity of our function, that looks like this, is negative 1. Okay, so when it's under the radical, we divide by the variable with the biggest exponent. If it's not under the radical, we take the square root of that value from the denominator. So looking at the next problem, you might think that I just wrote the same problem twice. Well, I didn't. The difference here is that we are going to negative infinity. So just like we did before, because we're approaching negative infinity, when we take the limit as x approaches negative infinity, we put a negative out in front. And then we go to work just like we did before. So this is very much the same thing. Our denominator will be dividing by x squared. Our numerator will be dividing by the square root of x squared, which is still x. So it's going to look like this. Negative x over x. We're still going to have the square root of 4 over x squared plus x squared over x squared. It's basically the same numbers. So this reduces to negative 1. This still goes to 0. This still goes to 1. And what we get is the opposite of negative 1 over 1, which we know becomes plus a positive. So this approaches 1. So basically, as x approached positive infinity, the limit was approaching negative 1. As x approaches negative infinity, the limit approached 1. And if you graphed that on your calculator, it would look something like this. It's approaching positive 1 as it goes to negative infinity. It's approaching negative 1 as it goes to positive infinity. So that's what that graph would look like. Okay, so the next example, very much the same. You go ahead and pause that video, do that problem. Let's see if we get the same answer. So pause that video. Okay, how did you do? Hopefully you got the same answer I did, which is 1/3. So let's take a look at the next problem. And this one looks a little bit different, doesn't it? The difference here is that we have our radical in the numerator. So what we're going to do is very much the same process as before. In the numerator, we're going to divide by x to the 6th. In the denominator, we're going to divide by the square root of x to the 6th, which is x to the 3rd. So just because the radical's in the numerator doesn't change really how we do this. So we have the limit as x approaches infinity of 9x to the 6th over x to the 6th minus x over x to the 6th. In the denominator, we will be dividing by x cubed. Oops, x cubed. Just jumping the gun there. So what we get, the limit as x approaches infinity, let's look at how these reduce. So this reduces here. We're left with 9. This is going to approach 0. So we have the square root of 9 over, this is 1. This approaches 0, 1. Therefore, the limit as x approaches infinity is the square root of 9 over 1, which is 3. So we would write this whole thing out, x to the 6th minus x over x cubed plus 1, and it approaches 3. So the rules don't really change just because the radical was in the denominator. Turn the page. And notice the only difference here is that, we are going to negative infinity. So essentially all of the work would be the same. We're still dividing just like we did in the previous problem. We would just have a negative out in front. So when it was all said and done, we'd get the square root of negative 9 over 1. Or I'm sorry, the negative square root of 9 over 1, which would be negative 3. So we don't necessarily have to do all that work for this problem. It's very much the same. It's just going to negative 3. And again, you might want to check what that looks like on your graph. Okay, if you put it on in your calculator, you could see those two limits. Okay, so what do we do now? We have the square root of 9x squared plus x minus 3x. Well, you can obviously see my hint there. What we're going to do is we're going to multiply by the conjugate over the conjugate. Remember, we can't multiply by something that's not equal to 1 because it changes its value. So we will have the limit as x approaches infinity of the square root of 9x squared plus x, and then outside of the radical we have minus 3x. And then we're going to multiply it by the square root of 9x squared plus x, that's all under the radical, plus 3x. And we're going to do the same thing in the denominator because Again, that's how we multiply by 1. Even though it doesn't look like 1, it's equal to 1. And we're going to clean it all up. Now remember, when we have conjugates, we really just have to multiply the first and the last because the outer and the inner will cancel each other out. So the first multiplied together give us 9x squared plus x. Outer and inner cancel each other out. We have negative 3x times positive 3x, which is negative 9x squared, all over the square root of 9x squared plus x plus 3x. Looking at this, you can clearly see 9x squared and negative 9x squared will cancel each other out. So a little rewrite here, we have the limit as x approaches infinity of x over the square root of 9x squared plus x, and then plus 3x outside of the radical. And if you think about what we did earlier, when we're inside the radical, we divide by the biggest exponent inside the radical. Outside, we take the square root of that value. So that leads us to this. The limit as x approaches infinity of x over x, and again, that's because the square root of x squared is x, over the square root of 9x squared over x squared plus x over x squared. And then outside of the radical, we have plus 3x over x. Okay, so again, outside of the radical was just by that reduced, that simplified value square root of x squared. What does this become? What does this approach? The numerator approaches 1. The denominator, these will cancel out. And this approaches 0. And then these will cancel out, so it will approach 3. So let's look at what that looks like. I'm kind of running out of space here. We will have 1 over the square root of 9 plus 0, so the square root of 9, which is 3, plus 3, which is 1 over 6. Okay, so not too bad for that one. Okay, not too bad, just a little bit more with the radicals. And again, we couldn't just drop infinity in here, so we had to multiply by the conjugate. All right, last couple of examples. We're going to put some things together. So notice I'm asking you to evaluate the limit as x approaches positive and negative infinity. Well, basically, you have to do 2 separate limits. So you'll do, oops, let me grab my pen. You will do the limit as x approaches infinity, and then you will also do the limit as x approaches negative infinity. And these are almost exactly the same, except for the fact that this one will not have a negative in front of it. This one will have a negative in front of it. The rules are the same though. We divide by the variable with the biggest degree from the denominator. So we will have x over x squared plus 1 over x squared. And our denominator will be x squared over x squared minus x over x squared minus 6 over x squared. Let's do this one first. We get 0 plus 0, which will be 0, over 1 minus 0, which means that this approaches 0. For the next one, it's going to wind up being the same thing. The only difference is, so when we go ahead and we do this, we would really write the same thing. I'm not going to write all that, just pretend. Okay, what we wind up getting is negative of 0 over 1, which is 0. So both will approach 0 from the left and from the right. Okay, if we were to graph this, by the way, if you were to put this in your calculator, we would see something like this. So first of all, let's go back to something we learned earlier, which is if we were to factor this, we would have asymptotes at -2 and at positive 3. And that's a little bit of old news right there. Graphing this would look something like this, just a quick sketch. And over here, as we approach negative infinity, we would approach 0. And as we approach positive infinity, we would approach 0. So that's what that function looks like. Okay? And by the way, what that means is we have, whoops, I should use a different color. We have a horizontal asymptote at x equals 0. Okay, I know that it goes through right here, and that's okay. It just means that the end result here, there is a branch that's approaching 0 here and here. Okay, so y equals 0 is a horizontal.